I'll bring this over.
Hamza, will you check on the teams? Okay, we're going to be doing the 2017 exam. If you haven't pulled up the QR code yet, I'll give you like 5 seconds to do that.
Thing closes.
Also, we're still figuring out the room situation. I don't know what the deal with that is. I think it's going to be 117 for sure. I think we were double booked with another professor, but we'll figure it out. Okay, we'll go ahead and get started. If I can find my shit. Okay. Okay, so we're going to start with the nomenclature. As always, best part about her exams is that they're structured, so you have the same sections every time and kind of know what to expect. So for nomenclature, with our alkanes, we just want to find the longest chain possible. And then we also want to find the most substituents possible. So sometimes this takes a little bit of trial and error. I know some people bring colored pencils, so if that helps you kind of like differentiate between your options, definitely go ahead and do that. Or you can just erase like I would do. So I'm just going to start from the left of this molecule and just start numbering to the right. So I'm just going to go 1, 2, 3, 4, 5, 6, 7. So that's a 7 carbon chain, not too bad. If we branch off from carbon 4 here and go up, we can get 5, 6, 7. So that's another 7 carbon chain. One more thing I'm going to try is starting from down here. So 1, 2, 3, 4, and then 5, 6, 7 either way. So it looks like the largest chain that we can make is going to be a 7 carbon chain. And so for a 7 carbon alkane chain, the parent is going to be heptane. So HEPT and then ane. If you're not familiar with the like number prefix for the alkanes, definitely get familiar with it because all of this stuff is going to compound. So you're going to need to know it for the future. The hardest ones are the first 4, like methane, ethane, propane, butane, because they're not quite like the numbers. But after that, like hexane, heptane, it kind of gets a little bit more straightforward. But definitely make sure you're familiar with that. So now that we've found the longest carbon chain, we're going to have to find the one with the most substituents. And so I'm going to go back and start with like the black numbering that we had. And I'm just going to circle the substituents we have coming off of that chain. So we have 1, we have 2, and we have 3. So not too bad. I'm just going to do, we have 3 for that color. And then other color, I did red. So then going up, we have 5, 6, 7. So here we have 1, 2, 3, 4, 5. So this has 5. And then if we number a different way, 1, 2, 3, 4, 5, 7. So we can get 1, 2, 3, 4. So that's not more than 5. Or we can get 1, 2. So that's not more than 5. So we're going to go with the one that gave us 5 substituents. And I will go ahead and renumber that so you guys can see. So that is going to be going kind of up to the right. So 1, 2, 3, 4, 5, 6, 7. And we have 1. Okay. So the next thing I'm going to do is I'm going to name these substituents. So just starting from the left, here we have a 1 carbon substituent. So that's going to be a methane or a methyl, sorry. The YL comes from when it is a substituent. Off of carbon 3, we have a 2 carbon chain, 1, 2. So that's going to be ethyl. And then coming off of 4, we have a 1, 2, 3 carbon chain, so that's going to be propyl. And since this one is 3 carbons just straight in a row, it's just going to be propyl. It's not going to be any of the fancy like isopropyls. So this one's just regular propyl. And then we have a couple of more methyls coming off of 5 and 6. We have another methyl and another methyl. Okay, so now that we've found our substituents, the next thing that we have to do is we have to look for the lowest numbers possible for those substituents in order for it to be the IUPAC convention. So again, just starting with the black numbering, going from left to right, the numbers we would get would be 2, 3, 4, 5, and 6. And then if we kind of start going from the right to the left, we'd get 1, 2, sorry, let me actually number it. 1, 2, 3, 7. So we get 2, 3, 4, 5, and 6. What did we say? We said 2, 3, 4, 5, and 6, and 2, 3, 4, 5, and 6. Okay. Okay, so whenever we have the numbers the same, going either way, at that point, it's going to go down to the alphabetical order. So basically, we want the B's, the E's, the C's, we want those to have the lower numbers, and like methyls or propyls, they might have higher numbers. So with the black numbering, we have a 2-methyl, we have a 3-ethyl, we have a 4-propyl, and we have a 5 and 6-methyl. We go with the red, we have a 2-methyl, we have a 3-methyl, we have a 4-propyl, have a 5-ethyl, and then we have a 6-methyl. So these are pretty similar, unfortunately, but the biggest difference that we have between these two is we have the 3-ethyl versus the 5-ethyl. Oops. So in this case, we're going to go with the black numbering because the ethyl, which is going to be our first substituent since it starts with an E, we want that one to have the lower number, so that's going to get the numbering that gives us that ethyl at carbon 3. Okay, so I'm going to erase all the red. Okay, so then now I can go over to like where I put my subs and just put the numbers there. So we had a 2-methyl, 3-ethyl, 4-propyl, and then 5 and 6-methyl. For stereochemistry, we don't have to worry about it because it's just an alkane. For this test, the only stereo you'll have to worry about is for cycloalkanes, if they're cis or trans. But again, this is just a regular alkane chain, so we don't have to worry about that here. So then the next step, we just have to put everything together. And then again, it's going to be in alphabetical order. So it's not the numbers, it's going to be the letters of the substituents. So our ethyl group would be first. Even though it's not at 2, it's at 3. Because it has the E, it's going to be our first in the name. So that's going to be 3-ethyl. And then M comes before P, so our methyls are going to be next. And whenever you have multiple of the same substituent, so we have 3 methyl groups, remember your number prefix. So however many there are, that's going to be that prefix. So first we're going to do the actual numbers that they're at. So 2, 5, 6, and then since we have 3 methyls, it's going to be trimethyl. And then our last substituent is the 4-propyl. And that's all our substituents, so we just put the parent name at the end. So you don't need to put like a space or a dash between the last substituent and the parent name. You just throw it on it at the end. So we have 3-ethyl, 2,5,6 trimethyl, and 4-propyl heptane. Any questions on that one? Okay, moving on. Here we have a cyclohexane in the chair conformation, very exciting. So whenever we have cyclo groups, just remember that if there's like a large substituent, the parent name is going to go to the one with the longest number of carbons. So if we number our cyclohexane, it's a hexane, so we know it's going to have 5 in that cyclic structure. And then we have our substituent here. So we're going to number this one just to make sure it's not bigger than our cyclo. So this one just has 4 carbons, so it's going to be less than the 6. So we're still going to go with the cyclohexane as our parent. So I'm just going to put that as our parent here. Cyclohexane. And don't forget your cyclo, because you will get points off if you forget the cyclo prefix. Okay. So then moving on, we just have to do our substituents now. So at this carbon right here, we have a 1-2 carbon chain. So that's going to be an ethyl. And then down here, we have a 1-2-3-4 carbon chain. That's going to be a butyl. And this one is actually going to be a complex substituent because it has a substituent of its own. So off of that 3 carbon, we have a cyclopropyl, 1, 2, 3, and it's in the ring structure, so it's a cyclopropyl. So we'll call that, it's 3 cyclopropyl because it's coming off of the 3rd carbon of that butyl chain. And then whenever we have a complex substituent like this, you throw it in parentheses in the main name that you have. So I'm just going to duplicate that. So we have 3 cyclopropyl. Okay. And then so those are our only 2 substituents. Before we get on to the stereo, let's just go ahead and number those real quick. And one other thing I'd like to point out is make sure when you are numbering off of the parent chain that you start from the carbon that is directly attached to the main chain. So for example, even though if we were not looking at the cyclo and we're just looking at, and we're just looking at the butyl chain, technically if we're just looking at the butyl chain, the cyclopropyl would be on a 2. But this is a complex substituent. It's coming off of the main chain, so we have to start numbering from the end of that chain that's connected directly to the cyclo group we have for the IUPAC convention. So make sure you remember that. So since we only have 2 substituents, we can only either get 1, 2 or 1, 2 for our numbers. So the numbers are going to be the same. So then again, we go to alphabet. So if we look at the red numbering, this would be 1 ethyl, and then the other one would be 2 cyclopropyl. If we did it with the black numbering, it's going to be just the opposite. 1 cyclopropyl and 2 ethyl. So in this case, we are looking at C or E. And so C obviously comes first in the alphabet. So this is going to be the numbering that we do. One other thing I'd like to point out for the nomenclature for things that have prefixes, you're only going to consider the prefix in the alphabet if it's intrinsic to that molecule. So you can think of kind of your structure. So cyclo or iso, those tell you the shape of that structure and the way that the substituent is laid out in space. So those are going to be intrinsic to that structure, and so you're going to consider those. So you would consider cyclo, you would consider iso or neo or whatever other ones. You're not going to consider number substituent prefixes, so di, tri, tetra, because those don't tell you anything intrinsic about the substituent itself. They're just telling you how many there are. So I think that's a key distinction to make. And if you have any questions about that afterwards, come ask me and I'll re-explain that. But so that's why we're going with the C and not the P, for example, in the cyclo. And that's why we went with cyclo for the cyclopropyl for our first number. I'm sorry, cyclopropyl butyl is the full 1-3-. There we go. Okay, so that one's going to get 1, and then our ethyl we said was going to be 2. So those are our subs, and then since we do have a cyclic structure, we do have to consider stereochemistry. And so this, when we have two groups, they're either going to be cis or trans. So cis is going to be they're on the same side. So either both on wedges or both on dashes, or both up or both down, if you want to think about it that way. And trans is going to be if they're on opposite sides. So if one's on a wedge, one's on a dash. So it's a little bit harder to see in the cyclostructure, or the chair conformation. So I'm just going to start up at the ethyl group that we have. So the ethyl group is coming off in the axial position, and so it's going to be pointing up. And then remember that the bond positions of the chair kind of like alternate. So if this ethyl is on the axial position up, then on the adjacent carbon, the axial position will be in the down. And then you have your equatorial. So our ethyl is in the up position, and then because the axial position on carbon 2 with our other substituent is down, then that means that this equatorial position that we have here is also going to be in the up position. So since these are both in the up position, this is going to be cis stereochemistry. So now we have all our pieces. We can just throw it all together. Stereochemistry always goes first. So we're going to do cis, and then our substituents. So 1, remember the parentheses for the complex substituent. And then 2 ethyl. And then our parent chain was the cyclohexane. Okay, any questions on that one? Yeah. So stereochemistry for cyclostructures, you'll either be given a cyclostructure like this where it's just in the normal hexagon. And so then you might see it as like wedges or dashes. In the chair conformation, it's a little bit more difficult to see, but you're going to be basing it on like the up and down positions of like the axial and equatorial. So if we just draw all the positions that we have, just have to remember that the positions alternate. So like the axial positions alternate up and down from each carbon because you don't want them all to be in the same space. They would be too sterically hindered. So for example, this axial is going to be up, and then this equatorial would be down. At the adjacent carbon, this axial is going to be down, and the equatorial is going to be up. And then if we look at the next carbon, oops, this axial is going to be up because it's, again, alternating with the other axial positions, and then that equatorial would be down. And then so on and so forth throughout the rest of the carbons. And so you're going to look at where each of your substituents are on that chair conformation. And so if they're both up or if they're both down, then that would be cis. If they're up and down or down and up, that's going to be trans. And then again, for the wedges and dashes on the regular hexagon, if they're both wedges, that would be cis. If they're both dashes, that would be cis. And if they're different, that would be trans. Yeah, so you'd have to be familiar with the chair conformation alternating bond positions. Yeah, you could, I mean, you could try to draw it out in the regular hexagon if you want, but you'd have to know the stereochemistry first to do that. So you kind of are forced to look at the chair conformation. Yeah, but you could, I just wanted to point out the regular hexagon because you might see it that way too, where it's just drawn as the regular hexagon instead of a chair. But yeah. Yeah, exactly. All right, I'm going to move on to the last nomenclature question that we have. Okay, so I probably should have just waited to bring this up, but this goes back to the numbers of the substituent versus the cyclostructure that you have. So again, we have a cyclohexane. So 1, 2, 3, 4, 5, 6. However, we have a pretty long substituent over here. So we're going to have to number that to make sure it's more or less than 6 to see whether it's going to be the parent or not. So this is a little tricky, but we're actually not going to start from this carbon here. Right now, I'm just going to like kind of think of them as like completely separated from each other and just find the number of carbons first. And so I'm going to start from this one at the top actually, because that's going to give us the longest chain. So we start 1, 2, 3, 4, 5, 6, 7, and then no matter which one of these methyls we go to, it'll give us 8. So we have an 8 carbon chain. And so 8 is obviously greater than 6. So we're actually going to treat the octane as our parent because it has more carbons than the cyclohexane. So now that we know that this octane is going to be our parent, I'm going to number it back and forth just to make sure I have the lowest numbers for my substituents. So we have the cyclohexane substituent and we have these 2 methyls. So we already numbered from left to right, so I'm going to do right to left. So we have 1, 2, 3, 4, 5, 6, 7, 8. So if we do the orange numbering, we get a 2, 3 dimethyl and a 7 cyclohexane. Cyclohexyl. And if we do the red, we get a 2 cyclohexyl and a 7,7 methyl. Dimethyl. So we have 2, 7, and 7 versus 2. I'm sorry, I don't know why I said 2, 3. 2, 2. 2, 2, 7. So 2, 2, 7 is going to be lower than 2, 7, 7. So we're going to go with the orange in this case. So I'm just going to erase the red. So we've already numbered our substituents. We have the 2, 2 dimethyl and the 7 cyclohexyl. We don't have any stereo in this case. There is a cyclohexane, but we only have one substituent on the cyclohexane, so it can't be cis or trans to anything else because it doesn't have like a neighbor. It's just when you have 2 groups on that cyclo structure that you can do cis and trans because it's a relationship. It's not individually describing each substituent. So we're not going to have any stereochemistry in this case. This one is Na. And so now we just have to put it all together. So then going back to the alphabetical priority, we're not going to be considering the di. We're going to be considering the M for the methyl. We are going to be considering the C in cyclohexyl because that is intrinsic to the structure of that hexane chain. So even though cyclohexyl is 7, it's going to go first because it has the lower alphabetical priority. So this one is going to be 7 cyclohexyl, 2, 2 dimethyl, and then our parent was 8 carbon chain, so octane. Any questions about that? Okay, I'm going to move on. If you have any questions about any of the nomenclature afterwards, just go ahead and come up. I did include, if you need some more practice with nomenclature, you're going to want to look at chapter 3, pages 1 to 3, and then page 8. Okay, so moving on to our facts section, sort of. So I put kind of like the sections for each of the questions, so you guys can go back and look at them if you guys are curious. Okay, so we have a boiling point question again. So if you're here yesterday, we talked about boiling point question. So in order to get a higher boiling point, we want a greater surface area. And so we can increase the surface area by having longer chains, because obviously the longer it is, the more surface area it has. Or we can have less branches. So to get greater surface area, we want longer chains and less branches. So we want a structure that honestly kind of looks like this one over here. It's long, it doesn't have that many branches compared to these two over here. But you can always number the carbon chains so you can kind of get a more concrete look. So we have a 1, 2, 3, 4, 5, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So since this one on the right has 6 carbons in a linear chain and it only has 1 branch, the other ones are shorter and have more branches. The one on the right is going to be our highest boiling point. And then comparing the other two, again, we can look at the numbers of the linear chain. So we have a pentane 5 carbon chain versus a butyl 4 carbon chain. To have greater boiling point, we want the longer chain. So this 5 carbon chain is going to have slightly higher boiling point than the one in the middle. Any questions about that one? Mm-hmm. Yes. Mm-hmm. So yeah, so we want longer chains and greater surface area for, longer chains, less branches for greater surface area and therefore greater boiling point. So more branching lowers the surface area and lowers the boiling point. Yeah, sorry. Okay, I'm going to go ahead and move on. Okay, so formal charge. Again, chapter 1, page 8, if you guys need more practice. So formal charge is going to be the number of valence electrons, and you can find that on the periodic table. So if we start at boron, I don't think that one says the column they're in, but boron is 3, carbon is 4, nitrogen 5, oxygen 6, fluorine F7. So that's going to be the number of valence electrons, kind of a shortcut. So boron has 3, carbon 4, nitrogen 5, and so on. So looking at this first one, we have a nitrogen. So we know that we have 5 valence electrons. And then to calculate the formal charge, we're going to subtract the number of electrons in the bonds it's making, divided by 2, and subtracting any electrons in lone pairs. And so what that means is we have 2 electrons per bond. So we're just going to divide that because the nitrogen is it only has half of those electrons. So that's why we divide the number of electrons in the bond by 2. Another way that you can think of it, and the way I personally think of it, is just calculate the number of bonds it has. So if it has 4 bonds, then your number would be 4. If you wanted to look at it the other way, it would give you the same thing. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the bond. And then you divide that by 2 to get 4. So you can either look at it as the number of bonds or you can do the divide by 2 method. So we're going to subtract that from 5. And this nitrogen does not have any lone pairs, so we just have a 0 there. So this is going to be 1. So that's going to give us a positive 1 charge. You can put positive 1 in the box. I think you'd be fine if you just put positive or if you just put 1. But I always like to just be extra safe and do like positive 1. Okay, so then moving on, we have an oxygen. So oxygen is in the 6th column, so it's going to be 6 minus whatever. We have 1 bond, so I'm just going to put that as 1. Or you can do 2 electrons in the bond divided by 2, which is 1. So 1, and then any electrons in the lone pairs. So we have 1, 2, 3, 4, 5, 6. So 6 minus 1 minus 6, that's going to give us -1. We're going to put -1 in the box there. Questions on that one? Okay, so we're looking at another nitrogen. So again, 5 valence electrons. If it helps you to draw out the structure fully, I highly recommend doing that. I know that sometimes in the condensed form, it can be a little bit trickier to see where everything is. Especially if you're practicing, you can just draw everything out so you can see exactly how many bonds something has. So in this kind of expanded structure up here, we have nitrogen in the middle. And then again, we have 1, 2, 3, 4 bonds. So we're going to have 5 minus 4 bonds, and then there's no lone pair electrons, so that's going to be 0. So we'd get another +1 for a nitrogen. And you don't have to like show the formula that you do, you just have to put it in the box, but definitely take your time, don't rush. So then we're going to be looking at aluminum. This one's kind of a weird molecule. It's not like nitrogen, carbon, or oxygen that we're always looking at. But if you look at your periodic table, which you will have one on the exam, we see that it's in column 3, so it's going to have 3 valence electrons. So we're going to start with 3. And then you can draw it out a little bit more here. So we have our aluminum here in the middle. And then this one has 3 Brs attached to it. And so following a similar logic, we're looking at the aluminum. It has 1, 2, 3, 4 bonds. So we're going to do 3 minus 4, and then no lone pair electrons, so that's going to be 0. So that's going to be -1. So this aluminum will have a -1 charge. Okay. And then for this last one, let's start with nitrogen, just because we've been doing it for every single one so far. So again, 5 valence electrons. This time we only have 2 bonds, so we're going to do -2. And then we have 1, 2, 3, 4 lone pair electrons. So 5 minus 2 minus 4. So that's 5 minus 6, which is going to give us -1. So that's going to be -1. And then we have carbon. And it does not have any lone pairs or anything like that. It's just these this bond to the CH3 and then the double bond to the nitrogen. So carbon is in the 4th column, so it's going to be 4. And then, 4 valence electrons. And then we have 3 bonds, so that's going to be -3. We don't have any lone pair electrons, so that's going to be 0 for that. So 4 minus 3 minus 0, that's going to be 1. So we'll put a +1 in the box for carbon. Any questions on formal charge? Okay, we'll go ahead and move on. Okay, so we're going on to structural isomers now. These ones can be tricky because you will be penalized for duplicate structures. So the way that I approach these questions is I like to letter my molecule, and it doesn't matter where you start from. It's not like nomenclature, it's just a tool that you can use to help. So just do it whichever way works best for you. So I'm just going to start from the left, and so I'm just going to call this first carbon that I'm looking at A. And then anytime I come across a carbon that's different, has a different connectivity, we'll give it a different letter. So if we look at A, going to the next carbon, we have B, because it has, it's connected to more carbons. And I'm just going to go left to right for now. So if we look at this carbon in the middle, this one is also connected differently than B. So we're going to call this C. And then if we keep going to the right, you'll notice that there's like this kind of plane of symmetry. And so both this carbon here and this carbon here have the same connectivity. They're connected to the carbon in the middle, and then they're connected to a couple of methyl groups each. So this one is actually not going to get a different letter. It's also going to be B. And so then following the same logic, if we keep going from, if we keep going to the right, this is also going to be a carbon A because it has the same connectivity as this one that we identified first. Okay, and then following that same logic still, this carbon is actually also going to be A because it has the same connectivity as the first one we identified. And another way that you can look at this is you can find any planes of symmetry. So we have this plane of symmetry here, we have this plane of symmetry here. For the B's we looked at, we saw this plane of symmetry here. And so if we keep following that logic, going down the structure 2, we'll also see that this is going to be B, and these 2 are going to be A's. You could also think about maybe like rotating the molecule. So if we just rotated this like 60 degrees, If you rotated it, you're still going to get the same structure. So if I say like this is my little point that I started at, I rotated it 60 degrees like this, that's going to be my little point. And so the structure is the same. So that's a couple of methods that you can use to identify if there's any duplicates. So then the next step, once we found all the different carbons that we have, is we have to do whatever it says the reaction is going to be. So in this case, it says monobromination. And so what that means is we're just going to replace a hydrogen at each of the different carbons and replace it with a bromine. So for that, we need it to have a hydrogen to give up. So make sure to watch out for any tertiary carbons or carbons that are connected to 4 other carbons. We would not be able to brominate this because we wouldn't be able to break a carbon bond, and we can't give carbon more than 4 bonds, so this would not brominate, but anything with a hydrogen would. So just keep that in mind. Again, if it helps you to draw out all of the hydrogens on the structure, I highly recommend it. So I'm just going to redraw the molecule. And so for our first monobromination, I'm just going to replace one of the hydrogens at this A carbon. So the way you're just going to draw this is you're literally just going to draw a little stick off of it and put a bromine there. And so that's 1. Again, we don't want to do any duplicate structures. So if we put a bromine here or at any one of these carbons, that would be considered wrong. So really make sure you're watching out for the duplicate structures. But we do know that B is different. So we can put a bromine there. And we know that we can put a bromine there because this B carbon is connected to 1, 2, 3 other carbons. So for that 4th bond, it has to have a hydrogen. So we know that we have a hydrogen that we can replace. So again, you're just going to draw a little stick off of that structure and put a bromine there. And so for our last one, again, if we're looking at carbon C now, carbon C has 1, 2, 3 carbon bonds. So in order for it to have the full octet, there has to be a hydrogen coming off of it somewhere. So for the monobromination, we'll just replace that hydrogen with a bromine. So that would be structure for C. So we have this structure here, which is like A. We have this structure here, which was B. This structure here, which was C. Any questions about that one? Yeah, so, yeah, not for this one. You just have to show where you put the bromine. It wouldn't be considered wrong though, so yeah. No, don't do that. That's getting a little bit farther ahead than you need to be for this exam. You will worry about stereochemistry like that in the future. But for this, the only way you'd know how to do that wedge and dash structure is if it was given to you. So if you're given a structure that was like, oh, draw the monobromination of, I don't even know, like carbon, and like, if it was something like this, like they gave you that stereochemistry, so then you could work with it. But this, it's just asking you to do a monobromination. It just gives you line angle. It doesn't give you any stereochemistry initially. Yeah. The only stereochemistry you'll need for this first test is the cis and trans for the cyclostructures. Any other questions on that one? Yes, that's a good question. So C in the middle, it is a CH. So they both are CHs. However, this C is connected to, if you want to look at it like this is your central point and this is a substituent or something, that's connected to a like a propyl almost, because that this part there's 3 carbons, whereas B, if you're starting with B as your central molecule, it's going to be connected to a methyl, and then like this whole big group over here. So that's different than what we looked at first. Yeah, that's a good question though. Okay, I'm gonna go ahead and move on for the sake of time. If you have any questions afterwards, go ahead and come up. So next we're gonna move on to hydrogen bonding in the pure state. So I think this is probably a relatively new concept. I think you guys probably just got to this, maybe. I might be wrong. It's kind of scary wording, but it's a pretty simple concept. Whenever it says pure state, this just means that you just have that molecule in the structure. So like think of each of these as kind of like their own separate question. So if we're looking at pure state for this molecule here, think of it as if you have a test tube with just that molecule. There's no solvent, there's no water, there's nothing else in it except that compound. And so in order to form a hydrogen bond in the pure state, something has to be oxygen, nitrogen, or fluorine has to be covalently bonded to a hydrogen. So if you remember this from like Gen Chem, you have like your hydrogen bonding intermolecular forces. And so that's going to be when you have an OH, an NH, or HF. You probably won't see this one just because it's an inorganic molecule, but OH or NH. So we basically need to see if the structure has an OH or if it has an NH. So if you look at this first one, we have an oxygen here, but this oxygen is only connected to this carbon bond. It does not have a hydrogen of its own. So this one is going to be a no. For this one, we do have a nitrogen. It has the carbon going up to the cyclostructure, carbon going down in the cyclostructure, and a methyl group. It does have a lone pair that's not John, but it does not have a hydrogen of its own. If it was something like this, then maybe, but instead it just has carbon groups. So this one is also going to be no. If we look at this one though, we see we have an oxygen and it is directly bonded to a hydrogen of its own. So this one can do hydrogen bonding in the pure state, so this one is going to be yes. Any questions on that? Because even though we have an oxygen, it does not have a hydrogen of its own. So even though it might look like there's hydrogens in the structure, the oxygen itself is not bonded to a hydrogen. Any other questions? Yeah. Yeah. Yep. So yeah, like I said, hydrogen bonding in the pure state is kind of a mouthful, but it's a pretty simple concept. Okay. I'm gonna go ahead and move on to the next question. So we have an acidity question. So these are going to be your favorite. So whenever we're looking at acidity for a compound, we have to look at the deprotonated state first. So I'm just going to show all of these in the deprotonated state. So we have an O-, we have a CH, and then this one is going to be a carbanion because it lost a hydrogen bond. And then on the right, we're looking at another carbanion, just in a little different position. So these are going to be the anions that we look at after we deprotonate. And so when we're looking at acidity, we want to find the most stable anion possible. And so this goes back to the CARDIO acronym. So charge, atom, resonance, dipole induction, and orbital. So you're probably just going to have to worry about these ones for now. But we basically just want to find which of these anions is going to be the best at holding that charge. So the obvious thing that we can see is that we have a O- versus two C-. And so automatically this O- is going to be our most acidic anion because Oxygen is more electronegative than carbon, so it's going to be better at holding that negative charge. So this OH is going to be the most acidic. So now we're left with 2 carbons, which is a little bit tricky. But the difference between these 2 is the resonance, actually. So we're going to be looking at this one and this one. So remember for resonance that you always want to shift from a nucleophile to an electrophile. So a source of electrons to an electron deficient state. So that's going to be, we're going to be pushing from lone pairs or double bonds towards other molecules. So for both of these carbon anions, we can actually resonate with the oxygens that they're adjacent to. So if we start on the right over here, we can push this lone pair towards the carbon double bonded to the oxygen. And in order to keep that carbon with only 4 bonds, we're going to kind of kick out the double bond of the oxygen. And we're going to form our first resonance structure. This double bond that we formed, we have that CH and a CH3. So now this carbon is satisfied, it has an octet, and we kind of gave that negative charge to the oxygen. So that's going to be that resonance structure. If we're looking at the other carbon, you'll notice that it's in between 2 of these double bonded oxygens. So we could push it to the left over here, or we can push it to the right over here. And so whenever we have a negative charge, you can stabilize it more by spreading out that charge as much as possible, basically. So essentially, the more resonance you can do with that negative charge, the more stable it will be. So since we have this one in the middle that has 2 resonance contributors versus the one on the right that only has 1 resonance contributor, the carbon in the middle is going to be the more stable of the 2. And the reason why we can't resonate to the right over here is because this carbon just has hydrogens. It doesn't have anywhere we can push those electrons to, so we'd either have to like break a bond or do something kind of weird. So we can't resonate over here just because it's a CH3. But we can with the oxygen. Yay. Okay, so that's going to be that question. Any questions? Yes. Yep. Exactly. So James or somebody correct me if I'm wrong, but I'm pretty sure cardio is kind of like in the order of preference for the rule. Yeah. So like, yeah, so it's almost like a checklist you can go through and see like which one you need to look at. But since oxygen is more electronegative than carbon, that's going to be the primary factor between the oxygen and the carbons. And then from there, you can kind of look at the trickier one, which is between the 2 carbons. Any other questions for that one? The Nu is going to be a nucleophile, and so that's going to be a source of electrons such as a lone pair or a double bond or triple bond. And then to the E is going to be the electrophile. So that's going to be a partially positive or a positive charge. So that's always the way you're going to do like resonance arrow pushing and mechanism arrow pushing. Okay, I'm going to go ahead and move on for sake of time. Okay, so we are not done with acidity and basicity yet. So again, we have our cardio acronym. And this one's going to be an acid-base question where we need to find which one's going to be the strong side and which one's going to be the weak side. And then the products of that acid-base reaction. So the first thing I like to do with these ones is I like to predict the products first. And so remember that acids are going to donate their proton and bases are going to accept the proton. So if we look on the left, we see that we have an SH and an NH. So this one is a little bit tricky because both of them have a hydrogen that could theoretically be deprotonated. So let's just look at both of them in their deprotonated forms. So the sulfur lost a hydrogen. So if we want to go back to the formal charge thing, sulfur is in group 6, so it's going to be 6 minus 6 lone pair electrons and 1 bond, so this is going to be -1. If we look at nitrogen, initially we already had a negative charge, and here we're going to be from 5 minus 4 lone pair electrons. Sorry, that's not right. 1, 2. So we can. Let me draw this out first. Okay. So we went from a negative charge, and then this is going to be 5 minus 1 in the bond, and then 1, 2, 3, 4, 5, 6 in the lone pairs. So this is going to be -2. So we went from negative to even more negative. And so this is just not going to be stable enough to be the answer, basically. So we're not going to deprotonate the nitrogen because it forms this like super unstable negative charge. And instead we're going to use the SH as our acid. So then if we just draw the product of that, we're going to be deprotonating it. So we're just going to be drawing that same anion that we already drew. So this is just going to be a S minus. And then we know that this is going to be our acid. So the nitrogen compound is going to be our base. And so in that case, it's going to accept an electron. So we're going to have CH3 and H2. And if you wanted to do the formal charge for this one, nitrogen, so 5 minus 1, 2, 3 in the bonds and 2 in the lone pairs. So that's going to be 0. So that's going to be neutral. So those are going to be our two products. And so now we just have to figure out which way the acid-base reaction is going to go. Also, one more thing. We do have this sodium in there, and that's going to associate with the negative charge that we have. Just because it's positive, it's going to be an ionic reaction. So since the nitrogen is now neutralized, the sodium is going to kind of float over to the negative sulfur that we have. So we're going to have that Na plus associate with that sulfur. And so just remember that that's an ionic interaction. It's not a covalent bond, so don't draw the sulfur attached to the sodium. That's not right. It's going to be the negative charges that are interacting. Okay, so now we have to figure out which is going to be our strong acid, strong base. So I always like to look at the acids because I just feel like I'm more familiar with them. So I'm going to look at the stability of the negative charge of the, I don't know what you would call them. So we're going to be looking at the stability of the S minus and then the stability of the N minus that we have. Okay, so if we go back to cardio, we know that sulfur is it's basically like oxygen, so nitrogen and then oxygen and then sulfur is in that same group. So sulfur is going to be more electronegative. So it's going to be better at holding a negative charge than nitrogen is. So that's going to kind of hint to me that this is going to be the strong, or I guess the more stable anion. If you wanted to go a little bit further, if you're not quite sure, we could also look at, we don't have any resonance that we can do, but we can look at the size of the atom. So the size of the atoms goes down, sorry, it gets bigger going down and to the left on the periodic table. So since sulfur is in the row below nitrogen, it's going to be bigger. And so it has more electron density and more shells and all that good gen chem stuff. So you can kind of think of that as being better able to hold on to a negative charge. So since sulfur is bigger, that's just another factor that's going to tell you that it's more stable as a negative charge than nitrogen. So overall, we know that this is going to be our more stable anion. So what that means in terms of the arrow is that we want to, if it's going to be more stable, that's going to be what the predominant form of the acid-base equilibrium is going to be. So there's going to be more of that S minus than there is the N minus. And so in that case, we're going to draw our arrow towards the S minus because the equilibrium is going to lie in the direction of that sulfur being the negative charge. So you could also think of it as being the SH is going to be a better acid, so it's going to dissociate more into that negative charge versus the NH compound we have over here. Any questions about that? Yeah. Yeah. I was saying you could look at the electronegativity. That's the first thing I would look at. And then if you're still not sure, you could go a little bit further too, just to double check or something. Yeah, so I probably should have not said that. So we have the S minus, that's going to be the more stable anion. And so that means that the SH is going to be the stronger acid because it will dissociate more into that S minus. So the SH is the strong acid, and then once it deprotonates, it forms the more stable anion. So you'll form that anion, and then it'll kind of stay there because it's stable as that anion. But yeah, always strong to weak. I always like to identify just one. So if you like to do bases or acids, you can do one of those. And then it's always going to be strong on the same side and weak on the other side. So if you're trying to do it and you get strong, weak, you have something wrong. Yeah. So anytime we have an acidic proton, that just means that that hydrogen can be dissociated from the atom that it's connected to. That's going to be whenever we have an electronegativity difference between that. So we don't usually see it for carbon hydrogen because carbon and hydrogen are pretty similar electronegativities versus some of the stuff that we've been looking at. So nitrogen, oxygen, sulfur, those have larger electronegativity differences. So that's where we basically find the proton that we dissociate first. So that's kind of like the first step. You identify the acidic proton. And then the next step is going to be, like I said, I like to find the compounds on the other side. So if I know this one's going to be my acid, I'm going to draw that as the product in the deprotonated form. And so you'll probably most definitely see a sodium ion or something in the question on the exam. And so the reason for this is just, I mean, in a real world situation, like you'd have a solvent or you'd have something in there. And so the sodium ion would kind of stabilize the negative charge. And so again, it's not a covalent bond, but the sodium will kind of associate with that negative charge as an ionic pair instead of just the negative charge being out in the world by itself, because that would be more unstable. So it's not super important to like the question itself, but it's just kind of to show that that molecule is not just like super unstable by itself. And then for the question, you'll just put the sodium wherever the negative charge is going to be. So usually it's going to associate with the other compound because that compound gets deprotonated and then forms a negative charge. And so again, that's just because it's an ionic interaction. The positive is going to be attracted to the negative, and they'll kind of just associate. Does that make sense? Yeah. Just compared to the nitrogen anion. So the sulfur anion is going to be more stable than the nitrogen anion. So that's going to be where the equilibrium lies, because you're always going to want to form the equilibrium towards kind of the more stable compounds. That's just kind of how the equilibrium works. Yeah, pretty much. No, yeah, that's it. Okay, I'm gonna go ahead and move on. Now we have a resonance question. And so I've mentioned this a little bit before, but whenever you have a resonance arrow pushing or a mechanism arrow pushing, what you're going to do is you're always going to draw from a negative source to a positive source. So a source of electrons to a positive charge or a partially positive charge. So again, that's just the nucleophile to the electrophile thing. So your nucleophile can be lone pairs, and then later you can look at double bonds and triple bonds too. Okay, so I'm just going to draw that lone pair on that nitrogen because that's supposed to be there. So we only have one positive charge here, but we do have a few sources of electron density. And just remember that you can only ever push the electrons to adjacent molecules. So I would not be able to push this lone pair here because this carbon is not partially positive or positive to accept that itself. So I'd have to start from somewhere closer. So I'm just going to start with kind of the top part of the molecule. So we do have this double bond that is adjacent to the positive charge. So I can draw that double bond towards the positive charge. And so what happens is we form a new double bond between those two carbons, but we actually lose the double bond that was attached to this carbon here. So that gets our new positive charge. And so then if you'll notice, the nitrogen lone pairs are now adjacent to that positive charge. So what we can do is we can push the lone pair towards that positive carbon. So we're going to form a double bond there. And in this case, our nitrogen is going to get the positive charge. And so you can go back and do your formal charge if you would like. So we have 5 minus 4 in the bonds and no lone pairs because we pushed that lone pair to make a double bond with the positive carbon. So this is going to be 1. So our new positive charge is going to be on the nitrogen. And I have not been doing this, so that's my bad. Whenever you're doing resonance, make sure you draw double-sided arrows and put the species in brackets to show that it's resonance. That's just the like standard convention. And resonance, you always draw double-sided arrows because resonance structures, they literally resonate back and forth super rapidly between the two structures. So we can't do anything more with this positive nitrogen. We could take the double bonds like back, but that would just be going in the reverse direction. And so we've already drawn that basically, so we don't need to draw it again. However, you do see that we do have a lone pair here that we could push towards kind of like the first structure that we have. So I can do that instead. So I'm going to push that double bond. And we're going to have a new double bond that we formed. This carbon is now going to be positive because it lost the double bond that it had. And then we also have another double bond now that we can push towards the positive carbon. So then this carbon over here is going to be positive since it lost that double bond. Sorry, my bracket's stuck. So we don't have any source of electrons from the top carbon here. We do have a double bond here, but again, it is too far away to do any resonance directly. So this is not acceptable. Don't do that. And again, kind of like this one down here, we could pull from the double bond on the right, but that would just be going in the reverse direction, so you don't need to draw that again. So in this case, these are going to be our resonance contributors. So once we've drawn all these structures, she's going to ask you to draw the important resonance contributor. And so that's going to, the rules for the resonance structure importance basically is going to be here, so you can go back and review that. But the number one priority to look at is going to be the octet rule. And so what that means is ideally we want all atoms to have their octet. So carbon as a positive charge does not have its octet because it's missing a bond. The formal charge 4 minus 3 in the bonds minus 0 lone pairs, that's going to give it this +1 charge. And it doesn't have its octet. So anytime we see a carbocation, we know that it does not have its octet. So ideally, we want to find a structure that has all the carbons with their octet, and maybe that pushes the positive charge onto another atom, such as like a nitrogen or an oxygen. But as long as they have the octet, it's okay. So again, positive carbon doesn't have an octet, positive carbon doesn't have an octet, positive nitrogen, positive carbon does not have an octet, and positive carbon does not have an octet. So each of these four structures here, they do not have an octet automatically because they have a carbocation. If we look at the nitrogen, we know that it has an octet because it has 4 bonds. So this is going to be our important resonance contributor. It does have a positive charge still, but that's okay because it has an octet. Any questions on this one? Okay, gonna go ahead. Oh yeah, sorry. That's it. Yeah, that's a good question. So if everything has an octet and like double, triple check that it does, the next thing would be like the electronegativity thing again. So for example, let's say we had 2 structures and they all had their octets, but the only difference was that one had a positive nitrogen and one had a positive oxygen. So in this case, we're going to look at the electronegativities. Both of them have their octet, so the only thing different is which one has the positive charge. And so in this case, since nitrogen is less electronegative, so more electropositive, I don't think that's like an official real term, but it's less electronegative, it's going to be better at having a positive charge. So in this case, you would go with the one that has nitrogen with a positive charge. So similarly, like if we had a nitrogen versus an oxygen negative, then we'd go with the oxygen as the negative charge because it's more electronegative. So that's the second thing that you would look at. Okay, I'm going to go ahead and move on. So considering the resonance contributors below, answer the following questions. Hybridization and angle and all of this fun stuff. Okay. So again, if it helps you to draw out these structures in like the full expanded form, I highly suggest you do that. Make sure you take your time on the exam. Try not to rush. So here we have a carbon. It's got 2 hydrogens, and it's got a bond to the nitrogen and a bond to the CH3 group. So it has 4 areas, I like to call them, and that's going to make it sp3, because all 4 of its bonds are going to be in the sp3 hybridization. Next, we have a nitrogen. So this nitrogen, it has 4 bonds, so it literally just has those bonds and not any lone pairs. So this one has 2 regions, and so that's going to make it sp hybridized. So you can kind of think of like sp as like the linear, sp2, that's like the trigonal planar one, and then sp3, that's going to be all 4 bonds. So next we have a nitrogen, and so this one has 2 lone pairs and a double bond. So this one is going to have 3 regions. So this one is going to be sp2. Okay. For this nitrogen, we have 1, 2, 3, 4 regions. So this one is going to be sp3. However, I tricked you guys. I'm sorry. Okay, so whenever you're looking at these resonance structure ones, specifically the hybridization, make sure that you're looking at both resonance contributors, because resonance for molecules, it's not either or. In the real world, the physics of that molecule is it's going to be both at the same time. So we like to draw the resonance contributors to show kind of like how the electrons might be shifting. But in the real world, the resonance is going to be, or the structure is going to be one thing. So we have to look at both resonance contributors to look at the hybridization. So going back to the structure on the left for this nitrogen, because you'll see that this is the one that we looked at over here. In this structure, it has 1, 2, 3 regions because it has a bond, a double bond, and a lone pair instead of 2 lone pairs and 2 single bonds. So over here, it's going to be sp2. And then with that same logic, if we look at this one and this one has 1, 2 regions, so this would be sp. And the one on the right has 1, 2 regions as well. So this one would also be sp. So honestly, whenever you do these questions, I'd probably look at each of the molecules that she identifies for both of them and find the resonance hybridization for both of them. And then what you'll do once you find both of them is you're going to go with the lowest one. So the reason for that is it's kind of like if you have 10 people you need to transport and you can fit 3 people in each car, how many cars do you need? You can't have like a third of a car. You need the whole thing. So you can't have like kind of more hybridization. You can only have less, if that makes sense. And James will probably explain it better than me, but you're just going to go with the lowest one. So this carbon one didn't change between the 2 structures, so that one's going to be sp3 no matter what. Nitrogen A, it was sp2 or sp3, so we're actually going to go with sp2. Nitrogen B, this one was sp versus sp, so that one did not change. So that one's still going to be sp. And then the one on the right, nitrogen C, was sp2 or sp, so we're going to go with sp. So, any questions on that? Not for this question. Yeah, you'll have a resonance question where you have to draw the resonance yourself. This one, she gives you the 2, and then you just have to compare them. You wouldn't. You'd have to do the hybrid or the resonance. For the sake of this test, like the previous question, she'll give you the 2 resonance structures that you'll need. So you don't have to worry about, for this question where it's asking about the hybridization, you won't have to worry about finding other resonance structures. Yes. So in the structure on the left, it had 3 regions, so it's sp2. But on the right, it only has 2 regions, the lone pair and the triple bonds. So the lower of the 2 is the sp hybridization in this one. And so that's going to be like the final answer. It kind of overrules the sp2. No, like she's going to give you 2. Yeah, she wouldn't give you 1 and then be like, oh, draw the other ones. Yeah. Okay, I'm going to go ahead and move on. So we did the hybridization, and now we have the Na, Nb, and C bond angle. So for the bond angle question, you're going to look at the atom in the middle to look at the angle. So you kind of have to do this one in steps. You kind of have to do A, then B, then C. So in the previous step, we identified that the hybridization for Nb was Sp. And so again, Sp is going to be linear. And so that's going to be 180 degrees. Sp2 is the trigonal planar. So that one's going to be 120. Kind of like a flat plane circle like sort of thing. So like 120, 120, 120. And then Sp3 is going to be the 3D shape, the tetrahedral. And so this one, it's going to be like slightly less than, I think you can do 109.5. But yeah, I think sometimes it's like slightly less or more depending on the atoms, but 109.5 is the one to memorize. And then because we said it was Sp, we're going to go with 180 for our answer. So then C are the p orbitals forming the Na, Nb, Nb, and C pi bonds in the same plane. So this is a excellent question. So we have B, we have A, we have C. So remember that for pi bonds, so double and triple bonds, the orbitals for those pi bonds actually like physically overlap. And that's kind of what gives the pi bond its strength. And so in order to maintain that pi bond, you cannot rotate those 2 atoms or else you'll break the pi bond. So those 2 atoms are kind of fixed in place. If we look at B and C, so we do have another orbital that's going to be creating the pi bond. We cannot have the same orbital contribute to 2 pi bonds. So if we have this first orbital like up and down, the same up and down orbital from B cannot contribute to an up and down orbital from C. Because you can't be in 2 places at the same time, and neither can atoms. So instead, a different orbital from each of those 2 will interact. So I'm actually going to. So instead of the green up and down orbital, we might have one that's coming off at an angle, like maybe perpendicular. So like side to side or like front to back or something. And so it's still a pi bond, so those orange ones or pink ones are still overlapping, but they're not going to be in the same plane as the green up and down orbitals because, again, that green orbital from the one in the middle can't contribute to both the atoms either side of it. And so, again, you can't rotate those pi bonds, otherwise they'd break, so they're kind of stuck next to each other at that angle. And so, no, they're not going to be in the same plane. Okay. Any questions on that? Because it's in the middle. Yeah. It's kind of like if you're looking at it on a line and you have like A, B, and C, and you're like finding the angle between the, I don't know, maybe that's a bad example. Okay. Okay, I'm gonna go ahead and move on. How many more pages do we got? Oh my god. Okay. So now we have our Newman projection question. So arrange the conformations. Luckily, we don't have to draw for this one. Arrange the conformations in order of increasing stability. So for Newman projections, the most stable is going to be in the eclipse formation. And so that's just going to mean on either side of the bond, they're kind of spread out as much as possible. So they're eclipsed. Staggered is when they're like kind of in the same orientation. So there'd be more steric hindrance. So unfortunately, all of these are, sorry, eclipse is the eclipse is the one where they're like at the same. Staggered is the one where they're like in between. Sorry. So these are all staggered. So unfortunately, we can't have one that's like obviously eclipsed that we can pick out. So the next thing that we're going to look at is we want the biggest groups to be as far away from each other as possible. So we see that we have a couple of big groups like isopropyls on all of them. And it's the same molecule just rotated, so we just want to find the rotation that's the best. So if you'll notice in the one on the left, both of those isopropyl groups are going to be directly across from each other, so that's going to be as far away as they can be. In the other two, they're next to each other, so that's going to be more steric hindrance. So, excuse me, the first one is going to be the most stable automatically because the big groups are as far away from each other as possible. So then looking between the one in the middle and the one on the right, we already know that both of the big groups are next to each other, so we have to see then what the big groups are next to as well. We have the big groups, and then on the left, we just have hydrogens, whereas on the right, we have a hydrogen and we have a methyl group. And so because we have the isopropyl methyl versus isopropyl hydrogen on either side, the one on the right is going to be more unstable because more big groups are next to each other. Even though it's a methyl, it still is bigger than hydrogen. So the one on the right is going to be the least stable, and the one in the middle would be in between. Okay. And then now we have to draw the least stable conformation in the box. So again, for stability, the most stable is going to be staggered when they're kind of like in between each other. The least stable is going to be eclipsed when they're like directly next to. So we're going to want to draw an eclipsed conformation. So the first thing that I would do is just draw out the little 3 spokes of the wheel. And then we want them to be in the eclipse conformation. So I'm just going to draw it like that. So we have the front bond and then we have the back bonds that are kind of in the same spot. And so then for the least stable conformations, we're going to want to put the biggest groups next to each other. So we have a isopropyl on the front and the back. So we can draw like the isopropyl groups next to each other. And then, so we have the isopropyl group, we have a methyl. So we're going to put a methyl on that front one. And then the other one was just a hydrogen. And in the back, we just have 2 hydrogens. So we're just going to draw those. Yeah. Any questions on the Newman projection? So in the middle, we have both of them have that big interaction between the 2 isopropyls. So we can't automatically make a decision there. So then what we have to do is we have to look at what each of those isopropyl groups are next to. So in the middle, the isopropyl is next to a hydrogen, and the other isopropyl is also next to a hydrogen. Whereas on the right, one of the isopropyls is next to a hydrogen, but the other one is next to a methyl group, which is bigger than a hydrogen. So instead of like a H isopropyl, so like these are the interactions. So H isopropyl and isopropyl methyl. This one is an H isopropyl and an H isopropyl. So we have this one and this one that are different. And so since the other one is the methyl is bigger. It's not huge, but it's still bigger than a hydrogen. So that's going to give us our answer. Yes. So the more interactions between bigger groups, the more unstable it will be. Yeah, sorry. Yeah, unstable. Okay. I'm going to go ahead and move on. Oh, to chair confirmation. Okay, so I've already drawn out my chairs. And everybody has their own way of doing these ones. What I like to do is I like to draw my chair. I like to draw all of the positions. And then I like to find my first group. So she's asking us to draw the more stable chair conformation for each of these structures. So I'm just going to look at A for now. And so the most stable chair conformation is going to be when you have the biggest group in equatorial positions. So our biggest group here is going to be this CCH3. So this is going to be like a T-butyl group. This is just a methyl, and this is just an ethyl. So this is going to be our big group here. So I'm just going to start by throwing that one on an equatorial position. And you can start from whichever carbon you like. I just always do this one. And for the T-butyl groups, you can just draw them as a T. That's fine. So that's going to be where I start. And I'm actually going to do that in a different color so you can see. Okay, so that's my T-butyl group in the equatorial position. And so now the next thing I'm going to do is I'm going to look at the wedges and dashes. So this T-butyl group I put on an up position at that carbon. So that means that all my other wedges on this structure are going to have to be in the up position at their respective carbons. It could be the same for dashes. So if I put it on a down position, then all the other stereochemistry of the same stereochemistry would be on the same thing. So if they're all dashes and I put the T-butyl on a up position, then all my other dashes would be on an up position. I know some people like to do down dash, and that's just kind of a way you can keep it more straightforward. But that's just up to you if you want to do that. So I put my T-butyl group on an up position. So I'm just going to number the ring. And again, this isn't nomenclature, so it doesn't have to be like correct. But that's just to orient myself going around the ring. So 1, 2, 3, 4, 5. I have groups at 4 and 5. So at 4, I need to put a CH3 on the up position. That's going to be at this axial position here. On carbon 5, I have an ethyl group. Again, it has to be in the up position because that's where my other wedges are. So that's going to be on this equatorial right here. And luckily, the ethyl group also ended up in an equatorial position. We do have a methyl group in the axial, but sucks. So then we're going to go to B. Okay. So this one looks pretty similar to A. The only difference is that between carbons 4 and 5, we just swap the position of the ethyl and the methyl. So again, I'm just going to start with my chair. I'm going to draw all the positions. And then I'm going to keep my T-butyl group. I still have to keep it in the equatorial position because it's still the biggest group. And then going around the ring. Now I have a ethyl in the up position, or sorry. I drew my T-butyl on the up position, so all my other dashes have to be in the up position. So the ethyl goes on the up, and then the methyl goes on the up at carbon 5. So that's going to be my structure. Okay. So those are going to be our chair conformations. And we can't draw it, like we couldn't do. I know we do have an ethyl group in the axial position for B. Unfortunately, we cannot put it in an equatorial position. Because what that would do is it would force our T-butyl group to be in an axial position. So my t-butyl group. So if this is down, then my t-butyl would have to be in down position. So it would have to be here, and that's in the axial. And since it's a bigger group, that's a no-no. So this is going to be what we're stuck with. So there might not always be the perfect, all the groups are in the equatorial. So just make sure that you're focusing on the biggest group. And then I'll just go back and erase the extra lines. Puts off. You could also just put hydrogens there if you want to. Mm-hmm. So the first rule is you're going to need to put the biggest group in the equatorial position if it's asking for most stable, because the biggest group has to be equatorial for it to be the most stable position. And then I just always check my stereochemistry with the big group versus the other groups. So if my big group is on a wedge and everything else is on a wedge, or if it's on a dash and everything else is on a dash, then I'm going to have to put them in the same position that I put them on the big group. So like here, I put the big group equatorial in the up position at that carbon. So if my other molecules are also on dashes like in B, then since I put the dash t-butyl in the up position, then I'm going to have to put my dash other groups in the up position. Yeah. Mm-hmm. If I had something like if this ethyl was in the wedge, since it's opposite from the dash, then I would be able to put it in the down position at that carbon because it's trans to the big group that I started with. So you'll start with your big group, and then anything that's the same as that one. So dashes, if you're starting with a dash for your big group, all the other dashes will be cis. If you're starting with a dash for your big group, the wedges will be trans, and vice versa. Yeah, that's what I would start with. I'm going to go ahead and move on. I know share conformations are kind of tricky, so I'll be here to answer questions afterwards too. So now we have to compare the two structures that we drew and figure out which one's going to be more stable. And so that's just going to be the one that has the biggest groups in the equatorial position. So between the two, we either have the methyl or the ethyl axial. So we want the ethyl to be equatorial, so we're going to go with A, because the ethyl, which is bigger than the methyl, is in the equatorial position, and the methyl, which is smaller, is in the axial position. So again, it's not perfect. Ideally, you'd want to put the methyl in an equatorial position too, but sometimes just the way it is, can't always control for it. So. Okay, so we're going to go on to the mechanism questions. I highly suggest you guys pay attention to this part because you will have to do this for every single test afterwards, and it only gets more complicated. So like I mentioned before, with any arrow pushing for mechanism or resonance, you're always going to go from a source of electron density to a source of electropositivity or positive or partially positive charges. So electrons to electron deficient, basically. So whenever I'm doing mechanism, I always like to identify my nucleophiles, kind of like we did for the resonance questions. So double bonds, lone pairs. In this case, radicals, you can also see because they are electrons. So technically they are like a source of electrons. I highly suggest you guys go, I don't know what I did. I highly suggest you guys go back to the radical reactions that you need to know. You will have to be familiar with the initiation, propagation, and termination steps because she could ask for any one of those for a mechanism or like a facts type question. And these ones are also kind of tricky because they're not like most other mechanisms. Since we're only dealing with single electrons at a time, we only use one-sided arrows whenever we're doing the electron pushing. So starting with this first one, we see that we went from a hydrogen at this position to a single radical at that position. And we went from bromine radical to HBr. So we know that the H and the Br have to come together somehow. And the way that happens is you have 2 electrons per bond. And so the electron from the hydrogen side of that bond is going to be kind of stolen away from the molecule with the bromine radical. And so the radical kind of steals that hydrogen and breaks it off of the compound. And we still have that 1 electron left in the bond, and that one's just going to isolate itself back towards that carbon. So in the product, we see that we left that radical there, and then we have a new HBr bond that formed. So that's going to be the arrow pushing for that, for the radical reaction. Moving on to B, always make sure you're checking like with the products, because that can give you a hint if you're kind of stuck on what to do. But try not to be too overwhelmed. Remember, always try to identify your nucleophiles. So in this one, we actually have 3 potential nucleophiles. They're all lone pairs on oxygens. We can see that we went from an OH on the cyclo structure to an OH-CH3. So we know that this OH in the cyclohexanol has to kind of take away a bond or take away that CH3 bond. So what's going to happen is the lone pair from the oxygen, either one, is going to come and it's going to basically steal that carbon. And that's how it's going to attach in the right-hand side. In addition, the bond that was initially between the oxygen and the CH3 on the left molecule, that's going to come back and isolate itself, kind of like the radical reaction, onto the oxygen to form our CH3OCH3. One other thing I would like to point out for this one is that because we have this oxygen next to all these carbons, and you can draw it from any one of these carbons. So you could draw it to that one or that one or that one. Not all of them, just one of them, but either of them are fine. Whenever we have an electronegative atom next to something like carbon, so in this case we have oxygen next to carbon, that's going to make the adjacent carbons just ever so slightly partially positive. So like the dipole notation positive. And that's because oxygen is more electronegative. So it's kind of stealing away electron density from the carbons and making the carbons partially positive. And I mentioned that because like we said earlier, we want to go from a electron source to electron deficient molecule. So that means like a positive or a partially positive charge. So in this case, you can see that we are indeed going from a source of electrons to a partially positive source. And so it's kind of like an ionic interaction where you have the positive and the negative, they come together, if you want to think about it like that. And so that's going to be the arrow pushing for that one. Next, we have one that looks pretty scary. We have a cyclic compound and then it somehow like unravels. Just remember, again, nucleophiles, electrophiles, keep it straight, you got it. And we can see that this iodine like actually attaches itself to the carbon structure. So again, we have this oxygen connected to some carbons, so these are going to be partially positive. And so this iodine, this negative iodine, the electron source, the negative charge, is going to attack one of those partially positive carbons. And similar to the previous question, that bond between the oxygen and the carbon is going to get kicked out and be localized onto the oxygen. So if you want to draw it kind of the way it looks here initially, so we have oxygen, hydrogen. So this is the bond that we broke right here. And it was replaced with the iodine bond, and the bond that we had initially is localized onto the oxygen as a lone pair. And then that's how we get the linear chain here. If you want to double check, I always recommend this, especially for later mechanisms. Just number them to make sure that you didn't lose any atoms. So I'm just going to start numbering 1, 2, 3, 4, 5. So we have 5 carbons. 1, 2, 3, 4, 5. 5 carbons, so we're good to go. So that's going to be the mechanism for that question. Yes, because we're doing a full lone pair or a full bond versus the radical in the first question. Okay, so that's going to be all of our questions. I wanted to point out a few other important concepts I think might be asked for on the exam. Depending on how far you guys get, you might be asked a bond dissociation energy question in the facts part. Free radical halogenation, which is kind of like the mechanism we talked about for 11A. And then reactivity of radicals, carbanions, and carbocations. Like I said, depending on how far you get. And those are all like the chapters and pages that you can go look to reference. So if you guys have any questions, I'll still be here for a little bit. Other than that, you guys are good to go.
That means the fair game back in the exam, so thank you guys for studying.